Well, I want to thank the Kieval committee for the invitation and for the chance to visit Humboldt State University. It's my first visit, and I hope it won't be my last. I've really enjoyed the day. You have a beautiful campus. The talk this afternoon, I had a great reception and had a wonderful conversation with the undergraduates and graduate students here. It's been a real pleasure so far, and I'm looking forward to meeting some more of you. Let's see. What I wanted to talk about today is a subject dear to my heart. I was trained as a differential geometer, which means a combination of geometry and calculus, or I usually tell people calculus on curved objects. And people often ask me why do we study calculus on curved objects? And beyond the usual answers in terms of applications to computer vision and modeling of surfaces or general relativity and so forth, there's a fundamental underlying reason that I wanted to try and say something about today, tonight, which is that geometry, the way we started thinking of it already over 2,000 years ago, has dominated in many ways the way we think about the new developments in mathematics, and it keeps being reinvented and extended into new areas. And I wanted to talk a little bit tonight about sort of what underlies why is geometry so successful in both application and it's finding new ways to help us solve problems. Of course, the place where we typically think of geometry in the modern sense starting is with Greek geometry in terms of the axiomatic approach. Of course, people have been doing geometry for years before that, many years before that. There's lots of evidence both in China, in Sumer, in India, in Egypt. Spherical geometry was already understood to some extent in Egypt before the Greeks. There were lots of things where people sort of practical geometry, so to speak. But it was the Greeks who really thought of trying to pare things down to their essentials and try to build things up logically from as small a foundation as possible to get a comprehensive way of looking at geometry. And they took as their elements in some sense what one might think of as the most symmetric objects you can think of. That is, things like lines and circles, spheres, cylinders, objects that had a certain amount of symmetry to them, and they used that symmetry in sometimes very subtle ways to help build up their picture of what the natural world looked like. For example, one of the critical things in their system of axioms were the axioms of congruence, which described how to compare two things. And in a certain sense, underlying that notion was, and it shows up in Euclid several times, is sort of the hidden picture, the notion of being able to line up two things, or actually being able to compare two things by a motion, by a kind of rigid motion. Even though there's no explicit axioms that deal with rigid motion in Euclid, sometimes you see hints of it in the proofs. For example, in his proof of side angle side, there's actually a kind of a comparison that looks like superimposing parts of one triangle over another. And the whole idea of how you do that superposition was something that wasn't in the axiom systems, but it was so much a part of the way people thought about things that it was hard for people to realize until later that actually was kind of a slip from the axioms. But even though Euclid did turn out to have some flaws along those lines, places where hidden assumptions crept in, it was really the model for logical development and axiomatic approaches to things for over 2,000 years. And the effect that it had of embedding symmetry into the way we look at the world was very important. And the case I want to make tonight is that use of symmetry is still still playing a very fundamental role in the way we understand models of the world around us. Jumping forward about 2,000 years from Euclid, Newton, in fact, I mean, just to get a sense of how influential that was, when Newton wrote his Principia Mathematica, he deliberately modeled it on Euclid. That is, it's written as propositions and very carefully done in the style of Euclid, avoiding the Descartes' algebraic treatment. You won't find coordinates in Newton, for example. It's everything is done more or less the same way Euclid tried to do things, and because he felt that this was actually the way one would actually establish something, rigorously, was to have something at least in the style of Euclid, and he thought of the laws of motion that we think of as one of his big contributions, and universal gravitation as sort of the axioms to start out with in understanding physics. Just to give a brief example, and I'll come back to this. I'll revisit it after when we get a little further on in the story. I just want to mention, let's see, I guess we don't have a pointer, a laser pointer or anything like that, right? I didn't think to ask for that, but that's okay. I think most people will be able to follow this. Or is it? Can you? Yes. Actually, you can do this. You can see this, right? Okay, great. For example, the mass times acceleration, in the universal law of gravitation, first of all, the laws that say the mass times acceleration is equal to the force acting on the object, and for gravitation, that force is proportional to the masses divided by the square of the distance. This is a unit vector pointed in the direction from the mass y to the mass, from the mass at position y to the mass at position x, or from x to y. That's this is the force as a vector and equals to the mass times the acceleration. Similarly for this, these are the equations for two bodies gravitating together, right? According to the universal law of gravitation. And second order differential equations like this, if you just write down a random set of second order differential equations, you almost can't do anything with them. It's very hard to tell what kind of qualitative features they're going to have or what kind of properties they're going to have. But these equations are very special in the sense that if you one thing you notice right away is that if you just take the mass of the body at x times its velocity plus the mass of the body at y times its velocity, that's the total momentum, the linear momentum. That's constant because, of course, if you differentiate this, the masses are constant. If you differentiate it, you'll get this guy plus this guy, and these two, and the right-hand sides are obviously negatives of each other. So it's not surprising that the derivative of this side is 0, which is the same thing as saying it's constant. That's one thing. Another thing that you'll notice if you just differentiate this equation here, you'll get, and plug in the second order equations, you'll get 0 on the right-hand side. So that's a constant. That's the conservation of angular momentum. And of course, there's conservation of total energy, which says that the kinetic energy of the first body plus the kinetic energy of the second body, plus the kinetic energy of position, that is the gravitational potential, is a constant, the conservation of total energy. And the existence of these so-called first integrals of these equations, of these second order equations, is what actually tells us how to get information out of the second order equations. For example, it's not very difficult to once you have this information to show that the center of mass of the system is unaccelerated And so if you sort of change frames, which is again a symmetry motion, change frames so that the center of mass is not moving, then the two objects gravitate around that center of mass, orbit it past on ellipses that are where the center of mass is at one of the foci. Those things fall out almost directly from these equations just by algebra, whereas the second order equations don't tell you that. Unless you could find the first order equations, the second order equations wouldn't tell you that much. And in fact, it's being able to find these so-called first integrals of the equations that makes the two-body problem tractable. And on the other hand, if you go to three-body problem, any of you who actually studied the three-body problem, which is of course important for any space capsule that's trying to navigate between the Earth and the Moon, you know that that's actually a very difficult problem. And in fact, that our inability to solve those problems, the three-body problems, is one of the things that stimulated the study of what we call qualitative differential equations in the 19th century, and became a cornerstone of modern differential equations now. But the thing that's a little mysterious is, why do we have these first integrals here, and why don't we have more first integrals when you have three bodies? And one of the things I want to explain is why we don't have them. But to do that, I have to give another piece of the puzzle, which is to explain, where did the equations come from in the first place? When Newton wrote them down, force is mass times acceleration. That's the second order. They turn into differential equations, second order differential equations. But it's not so clear. It's not so clear how you would have arrived at those second order differential equations to begin with. There is a principle that turned out as a unifying way to understand all these differential equations, which comes from the calculus of variations. And just to remind you just a little bit about what that is, the problem is that you're given the variable, the unknown that you're searching for, is a curve. Typically, in this simple case, it's a curve in space, in space. The endpoints are fixed, and what you're trying to do is find a way to find the curve that minimizes a certain integral. And a typical example is, if you have a surface in space, say the surface is given by a graph z equals f of xy, and you want to know what's the shortest path on the surface that joins 2 points. You can write down the length of the path. So the path will be x and y as a function of time, and of course z will be f of that function of x and y. You plug it in to find the speed, which is x dot squared plus y dot squared plus the derivative with respect to t of that expression squared, integrated dt. That's the expression that you should be reading as this L here, up here. And you want to find the curve that minimizes that. This is called the classic geodesic problem of finding the shortest curve joining 2 points on the surface. And it was Euler in about 1734 who realized that the problem of minimizing something like this could be written as a differential equation. He was the one who derived this equation, which we now call the Euler-Lagrange equation, that says that if you're at a minimum for this, then it satisfies this, which is actually a second order differential equation, because you're taking the time derivative of this expression, which is also already involves the first derivatives. The exact form of this is not going to be so important, but I just want to emphasize that this problem of finding the minimum of an expression like this that involves one derivative actually turns out to be satisfying something, writing down a differential equation that involves two derivatives, the second order equation. By the way, people often wonder, why is it called the Euler-Lagrange equation? Because Euler found it in 1834. I think Lagrange didn't really enter the picture until almost 20 years later. And the reason was, it turns out that while Euler found this equation, his derivation of it was quite complicated. And it was after Lagrange had published a note, had written to Euler with an explanation. Here's a simple way of computing, of showing that this actually is the solution, that Euler then decided that this was the right way to do things, and started promulgating it. And so the name Euler-Lagrange sort of stuck almost not just as the equation, but the method of finding the equation. And nowadays we call it the Euler-Lagrange equation, although some, I guess, historical books often say Euler's equation. But anyway, the point was that there's this connection between these first-order integrals and second-order differential equations. A little bit later, Gauss, who was started on this problem by actually, he was hired by the German government to help improve their maps that would take into account the curvature of the Earth. And he got interested in this problem of how do you accurately describe shortest curves on a surface. And he began to realize that our definition of a straight line, Euclid said a straight line is a curve such that the points lie evenly among themselves, which is kind of has more undefined terms than defined terms in it. And of course, we often say a straight line is the shortest distance joining two points, but in a certain sense, that's a tautology. It's the definition of straight line. And what Gauss was interested in was saying, well, what if you really literally take that as the definition of straight line, that is the shortest curve joining two points for every surface, then every surface has a notion of lines on it. And you can ask, do the lines behave the same way lines in space, the lines in the plane behave? And in particular, he started asking questions to himself about can I find a surface such that the lines in that sense, that is the shortest curves joining two points, actually satisfy Euclid's first four axioms, but not the parallel axiom. That is, and he was actually able to find such a surface. And thereby discovered what's called non-Euclidean geometry. He was the first to realize that it was not possible to prove the fifth postulate. That is, you couldn't prove the parallel postulate from the first four because you could find a surface in which the first four axioms held and the fifth one did not. So there was this at that time. People like Kant were promulgating the idea that Euclidean geometry was a priori knowledge, that you could not imagine any other kind of geometry, that was just what there was. And Gauss, who knew different, was, even though he was probably the most famous mathematician of his time, certainly in the West, still didn't feel secure enough to speak up and say, wait a minute, there are other possible geometries, and Euclidean geometry is not necessarily ab initio, the geometry of the world. So he didn't publish his results until, until they were discovered by other people, and in which point, people went back and looked at his notes and found that in fact he had done the calculations and found the examples. There's more to that story, but unfortunately I don't have time to go into the whole thing. But he realized the power of this notion of minimizing some functional as the definition of straight lines, or the definition of the most symmetric objects, as a way of approaching a lot of different problems in the physical world and in abstract mathematics. His student, Riemann, took this one step further and said, and in a famous lecture in 1854, he proposed that we should not, that in fact we should go back to the beginning and think of everything, straight lines and circles, spheres. Imagine all the properties of geometry as being the objects that minimize certain functionals. That is, that we should sort of turn the process, what seems to us right now, on its head, and define things in terms of minimizing properties rather than define things axiomatically the way we've done it, the way Euclid had done it. And also around the same time, Hamilton proposed that the laws of physics could be stated in terms of minimizing functionals, so-called principle of least action. For example, the two-body problem, which I said I would come back to, if you imagine x and y as moving curves in space, subject to trying to minimize this quantity, the kinetic energy, actually minus the potential energy. You may remember the energy occurred with a minus sign here instead of a plus sign. It turns out that if you now compute the Euler-Lagrange equations for this functional, then you get exactly Newton's laws of motion. So what it says is that the things that we think of as this motion, which looks complicated as straight line motion. I mean, it looks very curved and complicated to our eyes. Is actually, in a sense, the straightest possible lines in a certain geometry. That is, if you're looking at curves that minimize a certain function, these functions under the integral sign are called Lagrangians after Lagrange's work, and this realization that the equations of motion could be reinterpreted as shortest curves somewhere was a big step forward, in the sense that they realized that you could now think of, instead of possibly complicated behavior in second order, you could think of first order geometries and look for the most symmetric geometries, and that touched off quite a lot of interest in this principle of least action. So why was it helpful to think this way? And let me back up just a minute and remind you of a couple of things about differential equations. The general differential equation, I don't know how many of you have taken differential equations courses recently or are about to take differential equations courses, but one thing I'm going to let the cat out of the bag for those of you who haven't taken differential equations courses, is that the first few courses you take, you'll learn how to solve a lot of differential equations. They'll give you lots of examples and say, here's a method, here's how to solve it, here's a class of equations, here's how to solve it, here's a class of equations. But what they won't tell you is that you're kind of playing in the garden, that as soon as somebody gives you a sort of random differential equation, your hope of being able to solve it goes out the window. So, yeah, nearly no differential equations that you write down are actually explicitly solvable. And not that, I don't want to make you despair and think, well, what's the point in learning techniques for solving differential equations if most of them are going to fail? But the simple problems actually turn out to be helpful for understanding qualitative features. But there's another deeper reason that I want to try and get to here. Like I said, you can't explicitly solve the general differential equation. Even the three-body problem in space, there's a tremendous amount of work that's done on this, just to be able to do celestial navigation. But we are actually able to learn enough about it to land a rover on Mars from here. So it's not, even if we can't solve the differential equations, we are able to learn enough about them to be able to do things like that. But the process like I said, most differential equations you can't solve, but if the equation admits a kind of any symmetries, if there's any group of motions that preserves the differential equation, it turns out that you can make progress in solving the equation. So for example, suppose you have a differential equation that's rotationally invariant in the plane. So what that means is that, so here's an example. So the velocity of x and y is a function of the distance times the position vector plus another function of the distance times the position vector rotated 90 degrees. And so what that says is that the velocity vector at any point, the velocity vector is some specific function of some specific multiple of this vector and the orthogonal vector. This is y minus x. And so the velocity is some specific, f times g here added at each point. And what that means is that since it only depends on the distance, the whole picture is symmetric under rotation. And if you have this kind of rotational symmetry, then you take this differential equation, that almost suggests right away that you should change variables. That is, you should look at the distance of the point from the origin and look at the angle that the point makes with the origin, y over x is tangent theta. And when you do that, this differential equation actually uncouples into two differential equations. One, a differential equation that only involves r, and one, a differential equation that once you know r, tells you you can find theta just by integrating. So the symmetry allows you to break the equation down into pieces. And this is one of the reasons that the two-body problem is solvable, whereas the three-body problem is not. The two-body problem is, well, the gravitation problem is invariant under translation and rotation, and it's invariant under time translation. And those things correspond exactly to conservation of linear momentum, conservation of angular momentum, and conservation of energy. That is, time translation corresponds to conservation of energy. But those are the only symmetries there are for this thing. So you get exactly seven pieces that you can break it down into, and so if you do this kind of breakdown, it looks like you could break it down into the motion of 7 pieces or 7 coordinates, but then you'd have no control over the remaining 5 because, two bodies moving in space, there's position and velocity for each of them. That's 6 components. 6 plus 6 is 12. You have 12 things, but you only have 7 conserved quantities. So you might think, well, there's no hope. You've still got this 5-dimensional differential equation to deal with. But for some reason, that 5, you can still deal with it. And I want to say a little bit about why that's true. And to do that, I have to bring in another set of actors, people that you may have heard less about. One of them is Sophus Lee, who realized in the 19th century that the symmetries of a differential equation or of a physical problem could be used as a way to analyze the problem that in a systematic way. And what he did was show, his idea was this. He said that if you have a system that's invariant under a change of variables, like a rotation, like this is, then if you look at the velocity of a small change in that symmetry direction, that velocity, that differential equation, for example, the equation rotating around the origin, if you go through this process, you'll find out that the first order change is exactly x dot y dot is the vector rotated by 90 degrees. If you study the symmetries by first linearizing them by looking at their first derivatives, he found out that you could systematically exploit those first derivatives to integrate the equations. And, well, he found a set of methods for doing it, but it was Emmy Noether who really saw what the connection was between that and Lagrangians. And the infinitesimal symmetries of a problem, as Lee described them, and the conservation laws that you see, for example, conservation of linear angular momentum, linear momentum, and energy. A lot of people think of Emmy Noether as being famous for commutative algebra, but that's what everybody first they learned about in the theory in rings and the work that she did in invariant theory and so forth. But in fact, if you talk to nearly any physicist and ask them what is Noether's theorem, they'll say, "Oh, it's the theorem that allows me to understand differential equations with symmetries." And it turns out that Noether made a very beautiful observation. This was before she became an algebraist. She made a very beautiful observation that tied the infinitesimal symmetries or the symmetries of a problem with the conservation laws. And this is a version. It's a version suitable for what I want to say tonight. Her theorem says that if you have an infinitesimal symmetry of a Lagrangian, so if a flow like this preserves a Lagrangian like this, then this expression, which only involves first derivatives, is constant on any solution of the Euler-Lagrange equations. In other words, every symmetry of the equation induces a conservation law. And conversely, it turns out that every conservation law corresponds to a symmetry. This is a kind of the theorem she proved is actually more general than this. This is the theorem for what's called particle Lagrangians, that is, Lagrangians for curves. But there's also Lagrangians for two-dimensional things and three-dimensional and higher dimensional things, all physical theories, in fact. And Noether proved the corresponding theorem for all those cases. She showed that in every case, a symmetry of the problem gives you a conservation law for the differential equations. And this is such a fundamental aspect of the way we understand differential equations now, and physicists understand physical models, that it's become a kind of yoga for understanding physics. And I'll say more about that in a minute, but here's an example of exactly of this, that, in fact, when in 1915, Einstein, what we call the general theory of relativity is actually a theory of a Lagrangian for the motion of particles in gravitational fields, and how the gravitational field itself evolved. It's a Lagrangian theory, and the important thing about this theory, and the reason Einstein cared about them was, first of all, the theory doesn't depend on coordinates, so it's invariant under change of coordinates, which makes it, and that's a kind of symmetry of its own. It's a symmetry under change of coordinates. It turns out that what it predicts is that light rays and small particles will follow straight line paths through where straight line is defined with respect to a certain Lagrangian, and that Lagrangian itself satisfies an Euler-Lagrange equation for a Lagrangian for theories, for what they call for Lagrangians. If that begins to sound like a little bit of double talk, in fact, it's a little amazing that it's kind of amazing that the theory itself is saying that the physical world minimizes a Lagrangian to predict how things should move in under that Lagrangian. And in fact, for example, the coordinate invariance so Noether's theorem applies in this case that says that the invariance under coordinates is what predicts that that matter and energy will be conserved, or the total, the matter, the stress energy tensor will be conserved, which is one of the things that made general relativity tractable and believable, for that matter. In fact, this relationship between Lagrangians, symmetries, and conservation laws has turned out to be so powerful and so pervasive that is almost an article of faith in physical theories, that you can't have one of them without having that you can't have two of them without having the third. And for that reason, there's a kind of the behavior of a physical, in modern physical theories, the behavior of the physical system is usually explained by finding a minimizing Lagrangian, and then any observed conserved quantities have to be explained by some kind of symmetry. Now, quantum mechanics blows this a little bit, but quantum theories are basically built on classical theories, and they have a classical approximation, classical limit, and those are theories that are built on principles of least action. So that brings me to one of the kind of mysteries in particle physics. For example, we know that there are a lot of conserved quantities. There are, charge. In addition to mass, there's charge, spin, charm, strangeness, and so forth. But if you look at the physical world that we see, there's not enough symmetries in the theories to explain those conservation laws, to explain why those things would be conserved. And so that is in the four-dimensional world we live in, or actually you usually, in most quantum physics, you sort of freeze time and think of, that is, you don't do it relativistically. There's not enough room in the world that we observe to have symmetries that would explain these conservation laws. But the belief is that there have to be those symmetries there. So where are they acting if they're not acting in our everyday physical world? And the way out of that is to suppose that space actually is higher dimensional than it looks. That is, there's we perceive a four-dimensional world, but in fact there are other dimensions that in which the symmetry variables, the symmetry actions can occur, whose conservation laws give us things like charm and spin and strangeness. And so typically, this is one of the reasons that physicists often suppose that the world is higher dimensional than we actually see it. So, for example, the one way to try to unify electricity and magnetism is to actually suppose that the world is five-dimensional, and the reason we don't see the fifth dimension is that the fifth dimension is in some sense takes its motion that's very tightly constrained. It's so the basic example is if you actually hold the physical string far away, it looks one-dimensional. But if you get close, you can see that there's actually transverse dimensions there that are very tiny. The models that would unify electricity and magnetism, or at least these Kaluza-Klein models that attempt to do it, assume that there's at every point of ordinary space-time, there's actually a circle. A tiny circle that points are not points, they're actually circles. and the symmetry that we see is actually a rotation in that tiny circle direction. I mean, the symmetry that explains conservation of charge, for example, is actually rotation in that tiny circle direction. And now, the standard model actually assumes that there's actually a very large symmetry group. This doesn't matter so much exactly what the name is. Those of you who know something about groups know that this is a 8 plus 3 plus 1 is a 12-dimensional group that acts on these extra dimensions to produce all the conserved quantities that we see in the standard model. And even larger groups have been proposed to explain the things that would unify all the four forces, although we haven't been so successful at that. I mean, 3 out of the 4, gravity always seems to behave very differently from the others. And the attempts to bring gravity into the picture seem to require more symmetries even than we see now. In fact, when you talk with the physicists and they say we don't know what the theory is, we don't know what M theory is or what string theory is, what they mean is that they don't know the Lagrangian. They know, they have an idea of what the symmetries have to be because they have to because they have to explain various conserved quantities. And the pattern of the conserved quantities tells them something about what the symmetry should be. But they don't know what the Lagrangian is. And it's sort of like looking for you try to look for something by looking for the properties that it has, and then you write down the simplest example of things with that property, and then check and see if that gives you the right answer. Is sort of the way they try to work towards it. And by sort of following that picture, following that principle, and observing, for example, this observed phenomena that it looks as though every heavy particle should have a light part. Bosons and fermions should be paired in some way, even though we don't actually see how they should be paired. That is the reason for predicting or assuming that there should be that supersymmetry should exist. This symmetry that would somehow or another exchange the bosons and the fermions. But in order for it to work out, you always have to sit down and drop the list of properties, sort of run through the possibilities for the Lagrangian, and if you eliminate all possibilities, then you go back to the drawing board and put up a new and larger space and keep going. This is roughly what unfortunately I can't give you all the details, but right now the current theories that would allow for all of these symmetries to exist and to be operating say that the world has to be either 10, 11, or 12 dimensional. That's what the current theories say. The 10-dimensional theory, but the extra 6 and 7 and 8 dimensions, 6, 7, or 8 dimensions, as they exist, they would also have to be curled up very tightly like this. They'd have to be very tiny 6-dimensional, 7-dimensional, or 8-dimensional objects that we perceive as points. That would be the things that would support the symmetric objects that we're trying to understand. And the 6-dimensional objects, the one way that I got involved in this story many years ago was, I guess, about 20 years ago. In fact, maybe a little bit, 21 years ago, I guess, was that a friend of mine and I were working on some problems about 3-dimensional complex objects, that is 6-dimensional real objects, that we wanted to understand, which are nowadays called Calabi-Yau threefolds. We were trying to understand certain mathematical properties of them, and wrote a paper about it. It's a kind of interesting, made some interesting observations, but the problem was that we couldn't do some of the calculations that we wanted to be able to do. Nevertheless, we published the paper about what we were able to do, and a few years later started getting calls from physicists saying we actually need this object. We need to know more about these objects than you were able to tell us. And then they started telling us and other algebraic geometers facts, conclusions that they'd drawn about these objects, these Calabi-Yau manifolds, that we couldn't prove. There were statements about these six manifolds carry these many rational curves of every degree and so forth. Things that in fact we could only do part of and didn't actually agree with our calculations. But then the physicists insisted, and we found out that in fact we'd made some mistakes in our calculations, and their predicted formulas were actually right. And that touched off a wave of interactions between algebraic geometry, differential geometry, and physicists that's continuing today. The geometry of the six-dimensional objects has become a huge industry now. There's these Calabi-Yau manifolds and their applications in algebraic geometry, and it's actually pushed us to develop new theories in algebraic geometry that we 20 years ago would never have dreamed that we'd have, because we wouldn't have known to look for it. So it's a case that physics has taught us a lot about things that we thought we knew purely as mathematics. In the meantime, a few years later, I got involved in studying the corresponding 7- and 8-dimensional objects that would show up. Again, purely for mathematical reasons. These, for those of you who know something about Riemannian geometry and Lie groups, these are the so-called 7 and 8 manifolds of special holonomy, G2, the exceptional group G2, and spin 7. That for purely abstract mathematical reasons we knew was interesting, but we couldn't say much about the objects themselves. But then the physicists started saying, well, actually, if we have to go to 11 and 12 dimensions, we'll need to know something about the 7 and 8 dimensional objects as well. And that's where Ed Witten and several of his collaborators began developing the theory of what they call M theory and F theory for the 7 and 8 dimensional objects that would actually unify the 6-dimensional theory, which is the string theory picture that we understand, that we're beginning to understand now. But the fact is that these, even the existence of these 7 and 8 dimensional objects turned out to be a real challenge to construct, and with a tremendous amount of work now, with a whole host of people, particularly I have to say Dominic Joyce in England, who was the first one to actually find the 7 and 8 dimensional objects that could possibly fit, that actually did match all the conditions that the theory required. We've developed now in differential geometry an understanding of these things that is largely inspired by the kinds of questions the physicists have asked, and while it's too early to tell whether or not these theories will actually yield a viable theory that will unify the symmetric and the supersymmetric theory, it's turned out to be a real boon for mathematicians. We've learned a lot from just the questions the physicists ask. They say, well, we need to know that it has this kind of property or that it has these kinds of sub-objects. And we'd say, well, we have no idea how you would prove something like that. But they say, well, try. And so we work on it, and we make some progress. Right now, the interactions between mathematicians and physicists is continuing at in this particular area is as active as ever, and is producing a lot of exciting mathematics right now. Probably one of the a book for those of you who are curious about hearing more about it by Brian Greene, The Elegant Universe, is now a few years old, but it's still a pretty good summary of what's of how mathematics and physics are interacting. The thought I'd like to close on, though, is that our conception of geometry as understanding the symmetries of things and using those symmetries to help us understand their applications in the physical world is, while it's broadened and deepened considerably over the last 2,000 years, it's still part of the same fundamental idea of being able to incorporate, of being able to understand how the symmetries of an object can lead to understanding its analysis. It's a much deeper subject than it was 2,000 years ago, but I think it's not something that Archimedes would have been very astonished to learn. So anyway, well, thank you.
Yes. Well, I'm just interested to hear you say, how much of this is motivated by what the physicists are asking, and could you sort of give your opinion on how that has been true in mathematics, say over the last 500 or 600 or 800 years? How much of what we as mathematicians do came from answering the question about physics?
A lot. I think honestly, it has to be said that a lot of the theory of the calculus of variations, a lot of our understanding of partial differential equations has really come from developing things that we got intuition for out of physical models. On the other hand, it's turned around the other way too. I mean, when Riemann wrote his famous paper on the hypotheses that lie at the foundations of geometry, he developed this, what we now call Riemannian geometry, and Riemannian geometry was absolutely essential for Einstein to develop the theory of relativity. It was, in fact, the thing that stopped him for so long. The reason there was 10 years between special relativity and general relativity was he had to, in some sense, begin to sort of reconstruct what Riemann had done enough to be able to ask questions of people and find out, oh yeah, so somebody has worked this out and I can apply it in this case. I can develop a calculus that doesn't depend on coordinates and that does, that does consider only geometric objects as its foundations. And so it was absolutely essential that Riemann develop Riemannian geometry before general relativity could have been discovered. Yeah.
Have you looked into any of the higher dimensional systems? There's the G20 theory that has 20 dimensions behind it, and they reach that number of dimensions by looking at particles that lacked supersymmetric particles. And have you looked into any of those higher dimensional systems?
I personally have not, but yeah, I know. I mean, there are lots of when you for one thing, supersymmetry has not actually been observed, right? I mean, it's conjecture but not observed, and there's reason to believe, as you say, that it might not apply to all particles, and so if you take as your assumption that it only applies here and so forth, then you can get you get different answers for what the symmetry should be, or the conjectural symmetry should be, and there's a lot of work done in all these different assumptions. I'm not the expert on those. I don't know how much, in some sense, new mathematics has come out of those, but it easily could, and I'm not aware of it. Right? Yeah. Yeah.
It seems like the higher dimensions, they're more on a micro scale. I'm just curious, as we go up in dimensions, does it become more and more finite?
The length scale gets smaller. That's right. Yeah, and one reason for that is that if it didn't get smaller in these higher dimensions, if it's going to be a viable theory at all, it has to match what we actually observe in the world. And if the curvature of these objects didn't get bigger so that they got smaller, then as the dimension went up, my understanding, and you really want to talk to a physicist about this, but my understanding is that if it didn't get smaller, we'd observe them. We'd observe these kind of effects at lower energies, at energies that we already can reach. And because we can't observe them, they've got to be pretty small. They've got to be well below the Planck length.
Because I heard that an object of a higher dimension were to descend upon us, we wouldn't be able to perceive them because it's not in the same dimension. So is that what you're talking about?
No, not exactly. I mean, one has an image of the following kind of thing, as though our world, you might imagine our world is four-dimensional. It's some sort of slice in some larger, higher dimension, and the other objects are sitting there just off the slice, and so that's why you can't perceive them. In fact, that's not the image you should have. What you should have is that the real world is sort of like this string that actually has a physical thickness to it, has some thickness to it, but the things that we're able to observe is really only the length along the string. We're not able to observe any of the transverse things. So what we think the world is only low dimensional, but in fact it's actually big dimensional, and what we think are points are actually more complicated objects. And we can't perceive them directly because it takes a lot of energy to concentrate anything into a small region, and so it's very hard to perceive. But the only, in some sense, what you could say is the evidence that the other dimensions are there is that if they are there, then we could write down theories that would look like what we actually see. Whereas if they aren't there, there's no room to have those theories. So.